So let's look today at conditional probability. Conditional probability is the probability of an event happening given that another event has already happened. So it's under a certain condition. Here's our notation here, and it's read as the probability of event B given that event A has already occurred. That notation there, we do use that slash line. Notice that A is the second thing or whichever event is given. It can also be rewritten as the probability of A and B divided by probability of A. So whatever your given event is, which would be your first one, given that A has already occurred in your notation, it's the second one after the slash. If you're finding your probability, it is the denominator. Limiting that size of your sample space changes the total and therefore can affect your probability. Let's consider how you would calculate the following. Number one, what's the probability that a randomly selected adult has lung cancer? How would we find that out? We would want to know all the number of adults who have lung cancer, and we would be dividing that by the total number of adults. Okay, so if we would just wanted to know the probability of selecting an adult with lung cancer, anybody with lung cancer out of my total population of adults. Now, number two, what's the probability that a randomly selected adult has lung cancer given that they were a smoker? This changes my situation, right? Now we're looking at the number of adults with lung cancer out of how many people were smokers, the number of adult smokers. So my sample size has changed. It's also given me a more refined probability. The first one, we were just looking at lung cancer out of total population of adults, find a number of adults to sample. And then number two, given that they were a smoker, this is a totally different probability because we've narrowed down our sample space now to just adult smokers and of those who has cancer. An Algebra 2 class was surveyed and asked, did you do a household chore last night? And the results are shown in this table. They're classified by male and female, and then yes or no. Now, what's going to be helpful for us is some totals. So I'm going to come over here to my table and add up a couple. The total number of people that said yes, they did a chore, 14. The total number of no's is also 14. My total males is 15, and my total females is 13. Now, total, everybody apparently in this Algebra 2 class, I'm going to add up two of my rows here and have 28 total students in that class that were surveyed. So number one, what's the probability that a randomly selected class member did a household chore, or notated as probability of did a chore? So this is going to be the number of students that did a chore over our total class, right? Just keeping it simple before we move on. So I'm going to look at all the people that said yes, they had a chore last night. There was 14 total. Out of the total number of students in class, we found there was 28. We can simplify that into 1/2. Half of the class did a chore last night. Number two, what's the probability that a randomly selected class member is a male? So we want number of males out of total students in the class. Our total males going side to side here. This was 15. We have 15 males out of 28. Number three, what's the probability that a randomly selected class member did a chore given that they were male? So here is that notation. We want probability that they did a chore given that they were males. So we are only considering the males in the class that did a chore. So I'm going to put in the top of my probability chore and that they are male. Out of my denominator, my population that I'm only looking at is the males. So just like the lung cancer, if given that they were a smoker, we only thought about those that were smokers if they had lung cancer. Same thing here. We're only considering the males in the class. So I usually like to put my denominator first. I like to focus on what group am I looking at. That given group, the males. So we're only talking about the males. There are 15 total males in the class. I am going to write that as my denominator. Now, out of that row that I just highlighted, how many of them did a chore? 7 said yes, they did a chore out of the 15. So the probability that a randomly selected class member did a chore, given that they were male, 7 out of 15. Number 4, what's the probability that a randomly selected class member is a male, given that they did a chore? We already have your notation written here. Probably a male, given they did a chore. Now, wait, Ms. Bryan, is this not the same thing we just did on number 3? Not exactly. It's a little bit different. Now we're only going to consider the people that did a chore. How many of them are male? So we are looking at if they are male and did a chore, out of all of those that completed a chore last night. So let's go and see all the people that said yes. 14 people said yes. Like I said, I like to make that my denominator first to consider the small population that I'm considering with our conditional probability. 14 people did a chore. Out of those, how many are male? 7. So we have 1/2. We have half a probability that a randomly selected class member is male, given that they completed a chore last night. Let's try the next section. In a class of students, the following data table summarizes how many students have a brother or sister. Again, totals are very helpful for us. So I'm going to add these up. I have 13 people that have a brother, 10 do not have a brother, 11 have a sister, and then 12 do not have a sister. Our total numbers here, we have 23 students total. So number 5, what's the probability that a student has a sister given that they have a brother? So this is going to look like the probability that they have a sister given that they have a brother. To calculate this, our numerator is going to be those with sister and brother out of the given population that they have a brother, right? Given that they have a brother. So we are only going to consider the people that said that they have a brother. I'm only looking at this column. My denominator is going to be 13. Of those in that column that said that they have a brother, who also said they have a sister? 5. 5 out of 13. So probability that a student has a sister, given that they already said they had a brother, 5 out of 13. Number 6, what's the probability that a student who has a sister also has a brother? Now, up until this point, all of our conditional problems had the word given. That's a huge clue that it's a conditional probability. This example number 6 does not have that word given. So if you don't see the word given, the first statement is that given sample group. So read it again. What's the probability that a student who has a sister, all the people that have a sister, go stand over there. Now, of those people that have a sister, raise your hand if you also have a brother. You see that? So this first statement is going to be your given. So for our probability, we want all the people who have a sister, and then our numerator, they have a sister and a brother. Kind of similar to what we did before, but we are looking at only the group that said that they have a sister. So this row here, there were 11 total people. So that is my denominator. That is the only group I'm concerned about, is those that have a sister. 11. Of those 11, who also has a brother? 5. So we have 5 out of 11 is our probability that a student who has a sister also has a brother. Let's look at number 7. What's the probability that a student who does not have a brother has a sister? Again, no word given. So that first statement there is our conditional sample group. What is the probability that a student who does not have a brother, looking at just those, has a sister? So I just told the whole class, hey, if you do not have a brother, go stand over there. Now, if you have a sister, raise your hand, right? So let's put this together. Our denominator is they do not have a brother. Our numerator is those that do not have a brother, but they do have a sister. So those that do not have a brother, that is this column here. There was 10 total. That is my denominator. Of those 10 people, who does have a sister? 6. So we have 6 out of 10, or we can simplify 3/5, a 3/5 probability that a student who does not have a brother has a sister. For number 8, the following table represents the highest educational attainment of all adult residents in a certain town. Number 8 says, if a resident who has a master's degree is chosen at random, what is the probability that they are aged 30, through 49 and round your answer to the nearest thousandths. So again, there's not this huge word of given jumping out. So our first statement is narrowing down our sample space. If a resident who has a master's degree is chosen at random, what's the probability that those with master's degree, are aged 30 through 49? So probability of 30 through 49 given that they have a master's degree. So we are looking only at those with a master's degree right here, 30 through 49, and that they have a master's. And then my denominator is my total people that have a master's. Let's see, total number. This table gives us that total. Fabulous. I'm only looking at the 2,441 population there that has a master's degree. Of those, who is 30 through 49? Now here's 30 through 39, and we will need to also add this next column. So we'll have 467 plus the 779 to include that total age bracket. This gives us 1246 divided by 2,441, or when I change it to a decimal, rounded to the nearest thousandths, is 510 thousandths. Now, this is just one type of this question from Delta Math. There is a variety of them. Maybe it's one row, one section for your conditional. Maybe it's like this, one row with two that you got to add together. Or maybe it's a column with one, or column with two, or maybe it's two columns that you add together. So read those carefully. There is a variation throughout Delta Math on that section. So just like in our last lesson, we can take the formula and we can rewrite it and evaluate it and solve for other pieces of our probabilities. So here's your formula again for conditional probability. If you have the probability of A given B, your given group is always the second part on that notation. You can find that by doing the probability of A intersection B. Hopefully you recognize that notation. If not, they're still using it very interchangeably. So learn intersection means the same thing as and, divided by the probability of B, or whatever your given value is. Your given conditional sample group is always your denominator, because they're going to interchange them here in our examples below. Maybe it's a probability of B given A. So just make sure whatever the given group is that you are dividing by that. Let me show you number 9. Given the probability of A, probability of B, and they gave us the probability of A intersection B, that means and, right? Find the value of the probability of A given B. So the probability of A given B, this is pretty straightforward for our formula here. It's the probability that both occurred divided by my given, my second one there, in the conditional probability notation is B divided by B. So let's fill that in. So the probability of A intersection B they gave us was 0.415 divided by the probability of B they gave us was 0.71. Notice they gave us another value that I didn't need. So don't overthink it. They're going to give you probably an extra value that you're not going to use. So that would simplify to give me the probability of A given B is 0.585. Rounded to the nearest thousandth. Number 10, given the probability of A, probability of B, again, the probability of A intersection B, find the value of probability of B given A. See, I told you they were going to switch the letters. Probability of B given A. This doesn't mean a whole lot. This is not the end of the world. We are still going to use the intersection, the probability of A intersection B. That order doesn't matter, right? Because if I want the intersection of A with B, I just want what they share. So it doesn't matter if it's intersection of A and B or B and A, it's still the intersection. But it's always divided by your given value. So make sure we divide by the probability of A. That intersection probability was 0.522 divided by the probability of A, 0.7, gives me the probability of B given A is 0.746, rounded to the nearest thousandth. Number 11, the probability of A is given, B is given, and the probability of B given A. Find the probability of A and B. Whew. All right, so they did give us this given probability. So let's start there. Now, if that is my given probability and I can work from there, I will need the intersection A and B divided by the given probability of A. So let's just see what we can work with. We did get the value for the probability of B given A was 0.7. We are looking for the probability of A and B, but they gave us the probability of A was 0.56. What will we do? Use your solving inverse operations here, multiply by 0.56 on both sides, which gives us 0.392 equals the probability of A and B, the requested value there. Number 12, the probability of A, B, and B given A are all provided. Find the value of A intersection B. Let's see what we can work with. They gave us this given probability. Let's start there. The probability of B given A would be equal to the intersection. Okay, so the difference between number 11 and number 12, they use the word and in number 12, they use the notation for intersection. Means the same thing, but always divided by our given. So I'm going to use A here in our denominator. Let's see what we've got. They gave us B given A was 0.8. We are looking for that intersection value, and the probability of A is 0.39. Again, oh no, what will we do? Just multiply by 0.39 on both sides. And that's going to give us 0.312 is equal to A intersection B. So take the values that you have. Now they're going to give you more than enough. Notice on all these problems, there was something we didn't use. They're seeing if you know your formula. And just always remember you're given, the second one that's listed in that conditional probability notation, that given piece is your denominator. And like on 11 and 12, sometimes we have to solve for it, and it's okay. So conditional probability is probability that is occurring under a certain condition. We are looking at a small sample group, like those that did a chore and then male or female, or those who have a brother but do not have a sister. So you're separating your population into a smaller group and then finding a probability from that. That is conditional probability. And then the last piece, using that formula to compute other probabilities. So try that, guys. Let me know if you have any questions. Probability is loads of fun, and I hope you enjoy. I'll see you later.